In the liberal arts fields, there's a variety of tracks famously called How to Read a Book, How to Read a Poem. These are guides for a reader to how to get more and more out of the literature that they might be studying or enjoying casually. It occurred to me a number of years ago that there was no such lecture, no such material on how to read an equation. Hello, my name is Professor Duncan McFarlane. I'm an electrical engineering professor here in the Lyle School at SMU. And what I'd like to talk to you about today are a few tips on how to read an equation. There's a huge volume of textbook reading, of journal paper reading, of manuals readings, of application notes, Wikipedia. There's a huge volume of reading associated with engineering. You'll need to learn to keep up efficiently. It's not uncommon when you're learning a new set of material to have hundreds of pages to wade through. You'll be swamped or very overly selective if you proceed too slowly or too inefficiently. Now, when you're just starting out in the field, for example, the way I was my freshman year of engineering, it's really tempting. I came from a very liberal arts background, and so when I began my first studies, my freshman year in college of engineering, I was much more comforted by the words on the page rather than the equations on the page. So I focused on, in my entirety, in those early years or early semesters, on the words of the paragraphs. And there were times, especially times when I was a little bit tired, that when I came at the end of that paragraph to an equation 6.2 or equation 3.1 of the textbook, I kind of even jumped over it. Or if I was feeling a little bit more worried about a test, for example, I would just memorize the mathematical equation. Now, when I read my huge volume, my huge stack of journal papers or textbooks or background material, I kind of do the reverse. I kind of ignore the words, and I kind of skip from equation to equation. I look at the equations first. And really, based on a lot of experience, based on some study in my past, current, present, I can almost understand what the words are going to say just from looking at the flow of the mathematics. If I recognize a wave equation, for example, I can pretty much guess that the paragraph around it is going to be talking about the derivation or the discussion or the applicability of that wave equation. So I really don't need to spend a lot of time on the words, and I can kind of study the equations. And if I'm trying to digest 2 or 3 sources, it's kind of common ground to look at the structure of the equations and then figure out, okay, this guy's doing about the same as this person is. Maybe he's including a couple of extra terms, and that's about it. So, leaping from equation to equation, and then go back and read the words while also trying to predict what the author is going to say, means that you're really learning what's going on. So, if you're going to focus on the equation, then there are some tricks and there are some techniques that you can use to allow yourself to dwell on the equation, allow yourself to thoughtfully consider the equation as your eyes are resting on it before you move from equation 3.1 to equation 3.2 to equation 3.3. So the goal of this talk is to learn to look at an equation and to draw some lessons from it. So look at the parts of the equation. What functions are used in that equation? What constants of nature or mathematics are used in the equations? Term by term, component by component of the equations, what are the units of each piece in the equation? Now again, I love to use MKS units, meters, Kelvin, seconds. They all work out brilliantly. It allows you to go from force to energy and understanding all the differences between those. And it's just such a nice and simple equations. But I do recognize, especially some of the physicists out there who love CGS and some of the Some of the older-fashioned engineers in our field do like to use feet and inches, British thermal units. But I think for a student starting out, just to simplify your life and convert everything to MKS units is just such a nice starting point. So let's take each one of these points. What are the functions in the equations? Well, simple equations are going to be polynomials. A linear expression, a quadratic expression, perhaps a fractional power, something to the 1/2 power, the square root of something, or the 1/3, something to the 1/3 power, or 1/x cubed, for example. So polynomials and fractional powers, those are fairly common, fairly straightforward functions. You can kind of get a sense of what a curve, what a quadratic is doing, what a square root is doing, and how one's maybe convex and one may be concave. And so those are our building blocks. Those are our simplest building blocks. Transcendental functions. These are functions that have infinite polynomials associated with them. They can be expanded in a series, a Taylor series, to include all infinite terms. Some of the familiar ones, and I say they're not magic or difficult or more difficult than others. They're just what we've started to study from high school on, are the cosine and the exponentials. And some of you more further along in your engineering studies recognize that those are one and the same. But cosines and exponentials are some of the transcendental functions. So cosines have a certain behavior. They're not monotonic. And exponentials have a very aggressive behavior, either aggressively growing or aggressively damping. And again, if you write a cosine of a complex argument, or you write an exponential of a complex argument, you go back and forth between those two. There are also transcendental functions, many out there, that are unfamiliar or maybe less familiar. But you'll eventually run across these, or may sometimes run across these. Hermite functions, Laguerre functions, Bessel functions, Newman functions, Airy functions. These all come up from certain types of studies, from certain types of problems, and they have their role, they have their place in them. Again, they're not harder or less hard than the cosines and the exponentials. They're just functions that you haven't spent as much time with. You can imagine a calculator that has a cosine button on it. So you enter in a certain argument and press cosine, and the calculator returns the argument, the cosine of that number that you typed in. There are calculators out there that have Bessel function keys. They're very rare, but they exist, and you can type in a number and press the Bessel function key and find out what that number is. More commonly, you won't even be messing with calculators these days. You'll be coding up a plotting package or a MATLAB code to introduce a cosine. You could also do the same thing with Bessel functions. So again, it's working with these in practice is neither harder nor less hard than working with cosines and exponentials. But again, they do require some judgment. They do require some experience. And one of the best ways to do that is to plot them. Is to go ahead and have a log of what the whenever you come up with a new function, whenever you're introduced to a new function in a classroom or a paper, you run to maybe the same Excel file that you've always had, or the same MATLAB set of files that you already have, and you go ahead and exercise them. You plot them. I can tell you, it's a lot easier to do it this way than it was when I was starting out, where you had to do it with a calculator and a pencil and a graphing pad. Now, be judgmental about these functions. Be judgmental. I like to use the term aggressive function versus a gentle function. A linear term is a fairly gentle function, especially compared to an exponential. If things get bigger linearly versus things get bigger exponentially, tremendously different consequences in the long run of the evolution of those equations. So I would refer to a linear function as fairly gentle, and I would refer to an exponential function as aggressive. And if you're looking at a larger limit, if you're looking at the limits of these equations, you should ask yourself, what's the strongest term in the equation? If I have a linear term added to some term that has an exponent in it, well, as that linear term, as the argument gets bigger, the linear term isn't going to matter. Or a 1 plus an e to the x. Well, if x is huge, I don't care about the 1. So again, who wins in these equations under certain limits? That helps you determine the judgment, if you will, behind the functional forms in the equation. There are usually constants in the equation. And at first glance, constants are just a number. And they should provide no real angst. Factors of 2, they matter to get the right answer, but it's okay. Factors of 1/2. But some of the fundamental constants, some of the mathematical constants and some of the physical constants actually begin to tell a story behind the equation, where that equation came from, what derivations were used to intuit or derive formally those equations. Whenever you see a pi, for example, there's usually some circle somewhere in the problem. Even if you don't see it, there's some circular symmetry or spherical symmetry buried in the problem that tells you why that pi is there. A famous example is dropping a pen or a pencil onto a floor that has a tile floor, and you ask the question, whether the pencil will cross the boundary of 2 tiles or not, and the probability of that has a pi in it. And if you think about it, a pencil is a straight line, and square tiles on a floor are square. So where did the circle come from? Well, when you drop a pencil, it can drop at any angle, it can land at any angle, and so that angle goes from 0 to 2 pi. Hence, there's a circle buried somewhere in that problem, and the probability answer has a pi floating around in it. K is Boltzmann's constant, and it converts a temperature to an energy, and that tells you that there's something from thermodynamics, the study of thermodynamics, in that problem. Very oftentimes you'll see a KT floating around the problem, and that'll have units of joules, and it will represent the energy due to the temperature of the system. Planck's constant, H, that comes from quantum mechanics. Anytime, perhaps in a semiconductor course or a physics course, anytime you see the letter H in there for Planck's constant, or sometimes H bar, then you know that somewhere somebody used quantum mechanics to derive that formula. The role of Planck's constant is very similar to Boltzmann's constant. It turns a frequency into an energy. So very often you'll see H multiplied by a frequency, H nu, to get energy. C, the speed of light, that's a clue that you're talking about an electromagnetics problem from Maxwell's equations, or perhaps a relativity problem in physics. The number 2.404 sometimes comes up, and it's an interesting number. And again, it comes from a special function that we're less familiar with, the Bessel functions. And that means that we usually have a cylindrical symmetrical system, a system with cylindrical symmetry. Or perhaps we're doing a cosine of a cosine, or a cosine of a sine, a frequency modulated signal. Now, another mathematical constant that comes into equations is the square root of -1. And these are sometimes, in mathematics and physics, this is often denoted as I. And in electrical engineering, it's often denoted as J. Almost the same thing, the square root of -1. And this is an imaginary number. It turns a number into a complex number, a number that has a real part and an imaginary part. And remember, the imaginary part is an actual very literal term. There's no such thing as the square root of -I. But it's a brilliant placeholder. It's a brilliant mechanism to track two independent quantities in an equation, the real part, or the in-phase part, and the out-of-phase part, or the quadrature part. So again, the fact that an I or a J is in the equation tells us something about an assumption or a substitution into a wave equation using one form of a math function instead of another. Now, look where these components are in the equation. And this is incredibly simple. Ask what's in the numerator and what's in the denominator. And as basic as this silly concept is, piercing glimpse into the obvious, looking at what makes an equation bigger or smaller is a good way to start developing your engineering judgment and intuition about the equation. If a term is in the numerator and it gets bigger, then the answer gets bigger. The equation gets bigger. If a term is in the denominator and that term gets bigger, the equation gets smaller, the answer gets smaller. And again, it's very, very basic, but it's a very simple thing to do, and it just sort of helps you glance at, it helps you dwell on, it helps you remain on that equation and consider it a little bit more intuitively. Play with the equation, kick it around a little bit. What does the equation do as variables in that equation get small, very, very large, or very, very small? If a quantity goes to 0, does the equation still go to 0, or is there some residual behavior left over with it? If the equation gets very, very large, do things blow up or do things get very, very small? That sort of tells you what you can do with that equation. And then another thing that's kind of nice is change out each piece of the equation for the MKS unit. So if you have a length term in there, x, a dimension x, pull out x and write meters in there. If you have a temperature, pull out t and put k in there. If you have an acceleration, pull out the acceleration and put meters per second squared in that term. And then what you can do, and again, you're doing this probably on a piece of scratch paper, what you can do is you can then cancel out the different lengths, you can cancel out the things that are the units, and you can get a sort of a sense of how things collapse down into a final unit for the answer. It's very satisfying if the units on the left-hand side of the equation match the units on the right-hand side of the equation. That gives you a little bit more trust that no mathematics mistake was made. Again, play with the equation. I don't know about you, but every time I see a closed form formula, I have this tremendous urge to take a derivative of it. What are the units of that derivative? Remember when you first learned about taking derivatives, that allowed you to take maximums and minimums, define the extreme points of the behavior of that equation. And that's very, very useful in understanding where does this equation hit a maximum, where does this equation hit a minimum? And let's face it, there can be multiple answers to that. There's another one that you can do, another way to play with the equation, and that is to perform a sensitivity analysis. This used to be called an error analysis and was required of almost every laboratory. So you would look at, for example, a component of the equation x, and x might be a nice healthy number. Let's say it's a magnitude 1 or 17. And then you might say, well, what happens to the equation if I put x plus a very, very small deviation or perturbation on that x, delta x? So in other words, if x is 17, what happens if I put x equal to 17 plus maybe 1/10? What happens to that delta x? And there's a whole lovely way of doing sensitivity analyses that allow you to separate out the first case from the perturbation terms, the second order analysis, and then you can see kind of the behavior of what happens as you perturb each of the terms in your equation. And again, it's very, very closely related to an error analysis, which is absolutely vital whenever you get into the real world, a real world measurement situation. Well, if you're going to take its derivative, you might as well take its integral. And you might ask the question, over what range should I be thinking about this equation? What's the minimum value of time and what's the maximum value of time that I'm interested in? Now, I want to just pause for a second and consider the difference between a derivative and an integral. A derivative measures differences. How much difference is one point relative to the point that's adjacent to it? The integral says, how much are these two alike? What's the same, what's the average, or what's the same about these points? So an integral is about celebrating the same, or it's very much an averaging technique, and a derivative is about looking for outliers or extrema. And again, that's a very interesting way to think in terms of the physical meaning of these mathematical concepts and the relationships to the equation that you're studying when you apply those very, very simple calculus techniques. Plot the equation. And again, you've got wonderful software packages, NuPlot, MATLAB, Mathematica, many online, many graphing calculators as apps on your smartphone. So plot it. Plot the equation. And this does a few things. It forces you to look at the range of input values that you want for each term in your equation, for each component of your equation. It forces you to say, what's a sensible minimum and what's a sensible maximum to consider for this equation? What is the range of what is the output? What's the minimum output and what's the maximum output? What choices are you making about the axes? Are you looking at a log? Are you doing it on a linear scale, or a log scale, or a semi-log scale? Do you want to compress many decades of information into one scale, or are you satisfied with, say, 1 to 10 or 1 to 100 on a linear scale? So there may be actually multiple plots, but that's okay. If you code the equation in once into MATLAB, you can easily pick different vectors to plot. Now, along about your sophomore or junior year in college, regardless of whether you're a mechanical engineer or a civil engineer or an electrical engineer, you're probably going to run across frequency analysis, and you're probably going to stumble onto something called the Fourier transform. And in the digital world, that's a fast Fourier transform or an FFT, and that allows you to plot the equation not in the time domain, but rather in the frequency domain, or not in the x domain, but rather in the momentum domain, conjugate variables. And so does it make sense? And it won't always, but does it make sense to plot this FFT? And again, what I recommend is that you save the plots, and eventually, one in one file on your computer, and eventually you have a pretty nice catalog of functions and plots and equations lined up there, and then you can start using them as building blocks for much more complicated analyses. Now, eventually, you'll be able to mentally plot the equation, but really, all that does is save a little bit of time and battery life on your laptop. Now, all these basics become more relevant, become more useful, become more pertinent when you start looking at more complicated equations. So all the things that we've looked at above, looking at units of measure, looking at limiting cases, looking at numerators and denominators, perform those analysis term by term of the equation. Again, be judgmental. Which term is most significant? For large values of the variables, probably one term is going to outweigh the others. And for small term values, it'll probably be a different term of the equation. So for small x or small t, which one wins? And for large x, large t, which one wins? Again, there's a little bit of a competition going on for the voices of the components of each of those of each terms of those equations. Shifting gears a little bit, one of the languages that we use in our derivations and our understanding is the art of differential equations. And when you look at a differential equations, the first thing that I try to do is I try to classify that differential equation. Is it first order, second order, or something else? That sort of tells you whether you're looking at simpler solutions or maybe oscillatory solutions. Is it ordinary or a differential equation, or is it a partial differential equation? Are there terms just d by dt, or is it a d by dx, d by dy, d by dz, or is the del operator floating around in there? Are you working with ordinary differential equations or partial differential equations? Is the equation forced or unforced? Is there a term that's not related to the derivatives that's driving energy into the system? Is the equation linear or is it nonlinear? Are there x terms in there or x squared terms in there? Are the coefficients in front of the derivative terms constant, or are they functions of themselves? Are they functions of the variable itself? If you answer each one of these questions has an answer for a particular differential equation, and so you can be left with a description or a classification of the differential equation, and that gives you an idea of how complicated or how difficult it will be to solve the differential equations, and it also gives you some idea of what techniques you'll bring to the table. If you have a partial differential equations, one of the ones that's very commonly taught is separation of variables. If it has non-constant coefficients and it's only first order, there's an exact and separable solution to that. If it's a nonlinear differential equation, you've got to get really lucky to be able to get a closed form solution. Only a handful of these exist, and so solutions to nonlinear differential equations exist, and so you'll probably have to run to a computer with your tail between the legs. I just want to make mention of the fact on the slide here of the various notations that go along of a differential equation. Some people use a prime or double prime to denote a first or a second derivative. If you're taking derivative of time, you sometimes use a subscript, f sub t or f sub x for spatial derivative. df dt is the most explicit way of writing it, and if you have the space and you have the time, it's probably a good idea to use that. And then sometimes for time, you just have an f dot on the top of it. So one of the complexities, again, about equations, in particular about differential equations, is that people use different notations. And you'll have to get comfortable with a variety of those. So once you've classified the equation, that sort of stimulates and spurs your memory banks. And you can ask the question, is it a familiar form? Is it a diffusion equation, which is second order in space and first order in time? Is it a wave equation, which is second order in space and second order in time? If it's a diffusion equation, it's going to have exponential dependencies or Gaussian dependencies. If it's a wave equation, it's probably going to have some oscillatory equations. For sophisticated differential equations, for more interesting subjects, you're probably not going to be stuck with a simple harmonic oscillator, but you may be stuck with a simple harmonic oscillator plus a couple of extra terms in it. In that case, you'd have a variation on a familiar form. And what that tells you is that means you can expect the solutions to sort of have some similarity to that of a mass on a spring or a pendulum or an LRC circuit, but there'll be some differences as well. So again, there's an expression that seasoned mathematicians and seasoned physicists will use. Can you solve the equation without solving it? Do you understand intuitively what the terms are doing, the second derivative term, the first derivative term, and so on? Now let me give you an example of a particular equation, just to sort of try out some of what we've been thinking about, or what we've been talking about so far. So here's an equation for the force between two charges. It's an electromagnetic charges equation. And it's a function of Q, and it's a function of R. So there's a charge Q1, there's a charge Q2, and there's a distance between them, R. So the force is dependent on each three of these quantities. As Q's change, the forces change. As R's change, the forces change. The force will change. So what are the constituents of the equations? Well, right away, we can say that there's the charges, there's a distance between them, and then there's also some constants floating around. So F, and then you also note on this equation that F is a vector, and I've denoted this vector with a little line above the F. There's many, many ways of denoting vectors, and that's just one of them. And so the vector has a magnitude and a direction, and so happily on the right-hand side of this I have a unit vector, A sub r, which tells me that the direction of the force is associated with the line between the two forces. Then I look at r squared, and I look at the role of Q1 and Q2 in the numerator, and then I look at the constants. So let's take stock in each of these specific quantities that comprise or make up this equation. The force has a meaning. It's an attraction. It's a repulsion. It's a vector. And we know now what the vector direction is. A force physically takes a mass and accelerates it. It turns a mass into motion. Classic F equals ma. So if I have a force, I should expect for a free particle to some amount of movement or acceleration. F has units. Force has units. Newtons. But newtons are kind of, it's a composite unit. It's made up of a lot of others. So if you distill that down into its basic MKS components, you'll have kilogram meter per second squared. And so it's, yes, it's a Newton, and that's nice, but it's much nicer to think in terms of kilograms meters per second squared, because let's face it, there's also, in the R term, there's meters associated with that. Another quantity that's in there, on the right-hand side now, are the charges. Q, Q1 and Q2. And these, in electrical engineering, are the electrons, the protons, or perhaps the ions. And what pops out of this, the relationship between F and electrical properties, is that in this equation we're mixing electricity with mechanics. It's a very deep insight. Whereas we're mixing up physics with a vector mechanics course, or two different physics chapters. And there are units associated with charge, and that they're fundamental units, and that's a coulomb. So there's also a distance, r, and that's the separation of the charges. And then remember we were talking about the movement of these charges, and so we can scratch in our head and say, wait a minute, will that change? Will that r change because of the force? Or have I taken these electrons and I've somehow thumbtacked them to the board, thumbtacked them to a piece of wood, and held them in space? The units of measure of r is meters. So again, we're keeping track of everything. So those are the variables that come in. We can change q, we can change q1, we can change q2, we can change r. Note that if I swap around the role of q1 and q2, the product doesn't change. That's a magical thing associated with multiplication. And we notice that r squared is in the denominator, so as r gets bigger, the force gets smaller. As the two charges are further away, that number goes down. So it's a reasonably strong function, but it's not out of this world. It's a polynomial that sits in the denominator. So now we're looking at the units, and we know that we have funny units on the right: coulombs per meter squared times a bunch of the units from the constant, and that has to equal newtons or kilograms meters per second squared. So somehow I've got to get rid of the coulombs, and I've got to add in some meters and some kilograms and some seconds. So we look at the two types of constants in there. One of them, epsilon, comes from the physics or the electromagnetics of the problem. It's the dielectric constant. It's the choice of the material that these charges sit in. Has units of farads per meter. And the first thing we think about on this is farads. Farads, that comes with capacitors. What the heck is a capacitor doing here? Answering that question teaches us a lot about the arrangement of charges and the energy and the electrostatic energies that's floating around with it. It also teaches us a lot about, if it's epsilon naught, some properties of free space. If it's epsilon, some properties of whatever the material we're working in. So that's more of a physics, electromagnetic constant. The other one, 4 pi, is a mathematical constant, or in fact in this case it's a geometric constant, a constant of the geometry of the problem. We remember that pi comes from circles. Circles that are rotated as a sphere. It comes from angles, it comes from trigonometry. And so in this case, if we think about this, we have some sort of spherical symmetry, which is why we not just have a pi, but we have 4 pi. Instead of thinking about radians, we actually think about a very strange unit of measure called a steradian, which is the analog of an arc, or analog of an angle, in 3 dimensions. So now let's go ahead and take a look at the functional form. We've gone through and we've done an inventory of the different pieces of the equation, and we can look at what's going on. So we'll start on the left-hand side, and we say there's a force there, and the force is a vector. It has a direction. Where does it point? We take a look on the right-hand side, and we find the unit vector, and we kind of can answer that in this particular case. Then you might look at the numerator. The numerator has the charges in it. The bigger the charges, the bigger the force. Notice the way the charges multiply. If I can interchange the subscripts, and so the electrons. If I've got two electrons that are repelling each other, why should those electrons care about our numbering system? An electron does. If I label an electron, your electron number 1, your electron number 2, the electrons don't care what I call them. Let's face it, someone else is going to interchange those anyway. So there's something nice about that. There's something nice and comforting about the fact that the electrons really don't care what we as engineers are labeling them. The individuality of the charges is lost when I multiply them together as well. And I can't tell which one is bigger. And that's a very interesting loss of information that comes from this particular equation. Let's go ahead and take a look at the denominator. We'll start with the constants. In this case, these constants provide a matching of the units from the right-hand side to the left-hand side of the equation. And those units help give us the physical context of this equation. The right-hand side, moving a little bit to the right, to the r squared in the denominator, this is the main functional dependence. It's quadratic, and it's faster. It's a faster decrease than linear. And we can ponder the question, now why is this quadratic? And what's far more interesting and far more philosophical, why exactly is it a power of 2? Why isn't it not r to the 1.99999 or r to the 2.0000001? Again, there's something really beautiful about nature when we get the math and we get the physics right. When I first gave this talk, presented this talk, some students came to me and they said, but Professor McFarland, you're always doing derivations in class. You've taught us how to study a function, but how can we study a derivation? Well, someday I may write a whole note about that, a whole lecture about that, but I have a few thoughts that I'll share with you right now. So, a derivation is made up of multiple steps, usually of rather simple math that carries you from one step to the other step. So you should write down in words, next to the next to the points of the math, what exactly you're doing on each step of the derivation. I'm multiplying both sides by 17. I'm dividing through by the cosine term. That's dangerous because the cosine can sometimes be 0. And a 0 in the denominator can wreck your whole day sometimes. What about for skipping the steps when you've studied the derivation, when you want to commit it to memory, you want to understand it better? Why don't you take a look at the equations and just line out the steps of the derivation that are obvious to you. And then on the next pass, fill in those steps with a very short description of what you're leaving out. And the idea is to be able to go from following a derivation to be able to doing it. And my old PhD advisor, who's not old but former PhD advisor, described it as pretending to do the mathematics, pretending to do the math. And I kind of like that phrase. I kind of like the fact that that's what we're trying to do. Is we're studying the derivation, we're not replicating it, we're not redoing it. We're just pretending to go through what somebody else has done the heavy lifting on. Now, one thing that students want to do, and most everybody wants to do, is whenever they see an equation, say in the middle of the derivation, they want to understand the physical situation of that equation. Sometimes that's possible, and comforting, and useful. But sometimes it's just not. Sometimes there's no real new physical understanding that comes from that particular step. There's no reason other than mathematics that you can do it to do a particular step and get to a particular part of the equation. And I point this out because a derivation employs the tricks and the rules of mathematics. And the math can guide you through a foreign territory. I sometimes describe this as you're going along in a countryside and you're looking around and you're seeing pastoral land with cows and fields and trees and so on, and you get one sense of the world around you. And then you go into a tunnel, and that's the mathematics being applied for mathematics' sake. We do these steps because we can do them. And we have no idea what's going on outside of the tunnel. We don't know if we're under a river, we don't know if we're under a mountain, we don't know what's going on in our tunnel. We don't have a sense of the world around us. Then we come out of the tunnel, and we might be right by an ocean. And we might be seeing a whole different landscape. We might be seeing the waves break against the beach. We might be seeing the restaurants and the bars that line this beach. And we have a completely different world understanding of the world around us than we did when we were back before the tunnel, back when we were staring at the cows eating the grass. So closing this out, in summary, take a big picture look at the equation. Understand, have I seen this or something like this before? You'll have to reconcile. Everyone has different notations. You'll have to reconcile that. Inventory the constituents one at a time in those equations. Look at the functional form. What makes the n quantity bigger or smaller, and how quickly does that happen? So, how to read an equation. Some tips, some thoughts, some comments. I do hope you find it useful. Thanks.